2003 period. So that time it was like direct interview basis,
Okay.
and
Interview
now
basis.
there is a common entrance. Entrance in the sense like they will call for, and we have a ISRO centralized recruitment board (ICRB).
Okay.
So through that they absorb.
Hmm.
But for PhD candidates, there is a separate call for also will come. So that is likely by direct interview.
Oh, okay. Direct entry is there.
Yeah. So there will not be any written test for PhD candidates.
Hmm.
So only that call for we have to look for likely. Then once it comes, then we can directly apply for it.
Okay. Okay. So, like, for that, we have to give some interview, right? Definitely interview will be
Yeah, yeah, that will be at our headquarters Bangalore, and with maybe interview experts maybe from IAC Bangalore, professors from IAC.
there. Oh, okay. Okay. ISC Bangalore. That's good. Uh, and like, how is the work there? Is it good? The culture and all?
Yes, yes, yes. Here we have what we can say dynamic systems, and
Oh,
that's why we are like though the launches are more,
hmm.
we have a good supporting system working here, which will support us for the activities. It is not like
Okay.
a single center only taking all the loads. More than
Okay.
say 10 centers across India, they will be developing the subsystems, and
Yes, sir.
everything will get integrated at our Shar or this Bangalore for launch vehicle and the spacecraft. Then it goes into launch that way.
Okay, sir.
Everybody will have their own growth profile here. Right?
Yeah, yeah. Yes, sir.
So that way it will be good. Like working ambience will never get outside like what we are having in Israel.
Hmm. Yes, sir. Yes, sir. So that's really good. Okay, then, sir. We'll see you for today's class.
Yeah, yeah,
Yeah. So for today's class, hello everyone. My name is Rohan, and this is the fifth session for the polymer reaction engineering class. We'll be seeing few problems which will help you solve the assignment number five. By now, assignment number six, the week six lectures have been released. I think the assignment is also out. So maybe one or two question in this might be related to that. So you will have to go through the course material for to understand. So
yeah.
that will be much. Yeah. Yes. Uh, so we'll go through this now. So our first question is, for an isothermal liquid phase second order reaction, P given Q, in a PFR, the ratio of the time required for 80% conversion to time required for 45% conversion is. So we have been given a PFR and we have been asked to see the time required for the 80% conversion to the time required for the 45% conversion, which is depicted by XA. And we know that the concentration can be written in terms of XA as like this, as follows. So if we have a concentration for, let's say, Ca, so that Ca can be written as Ca naught, that will be the initial concentration, uh, that is related to the fact that the consumption of initial concentration is shown in these expressions, that Ca naught multiplied by 1 minus Xa. Here Ca is the amount which is left over, and Xa is the conversion, and 1 minus 1 minus Xa will give you how much is left over, and we once we multiply that with Ca naught, we can get how much is the leftover concentration. So we can write it as such. So with that respect, this is a second order reaction. So you can see that, and on top of that, it's a PFR. Second order and a PFR, second order reaction and a PFR reactor. So the design equation for PFR is given as such. The volume of the reactor is equal to the molar flow rate with an integral going from 0 to the desired conversion, but and the integral term is dxa divided by the rate expression for the specified order of the reaction. So here what we have to do is for the minus RA part, we have to put in kCa power 2 because this is the second order reaction. And since this is the second order reaction, we have to insert that there and going from 0 to x. In first case, the x is given as 80% conversion. So x will be zero point 0.8. So we have to write down zero point 0.8 and then instead of kCa, we have to replace Ca with Ca naught. And here also you can see that on the left hand side, here the same expression is written as V by Fa naught is equal to integral xai to xaf. That is the initial to final dxa by minus Ra. So here we can see that if we are sending in some pre-converted feed, uh, as in like the feed has already reacted a bit, so we can write the initial conversion of the feed going to the final conversion of the feed. So in our case, we have been asked to go from 0 to 80% and from 0 to 45%. So we have to write down the similar expression for the same reaction in two different scenarios. So here we can see the consistency of the units V by Fa naught. V is the volume and divided by Fa naught. Fa naught here is the molar flow rate that is given molar flow rate per second. That will be given as moles per meter cube per second. So when you check the unit consistency here, we have V, that is the volume, and we have the molar flow rate right here. So we can see that to maintain the unit consistency, we have tau is equal to Ca naught. Ca naught is nothing but moles, and tau is the time. So we have this expression right here, and we have the relation for Ca is equal to Ca naught 1 minus Xa. So for a second order reaction, we will be getting the expression as K Ca square. So this expression will be put at the bottom right here in the minus Ra term, and then you put the Ca, substitute the Ca term, that is Ca naught 1 minus Xa whole square here in this expression. And once you substitute that here, we can take out the constant terms outside, that is the K and the Ca naught, since the initial concentration is constant. And then we integrate with respect to 1 minus Xa whole square, going from 0 to 80% conversion or zero point 0.8, we can write down. And similarly, for the next conversion also, we have to form the expression going from 0 to 0.45. And when we equate these two, we will get the ratio of the time required for the individual conversions. So here, without showing the arithmetic, the correct answer for this is 4.88. You can try it yourself, and if any other answer comes, we can discuss it later on. But this is how it is supposed to be solved. So that will be for the PFR. Moving on to the next question. Same question. If in the above question PFR is replaced with three CSTRs of the same volume, then the exit conversion of the reactant A is. Now,
One small clarification, Rapanji. Actually, this minus RA when we are for the earlier one,
yeah,
minus RA like K into CA square, and CA we are substituting with the CA naught into 1 minus XA
yeah,
whole square. And
yes, yes,
we have to take it to this tau, right? Tau
hmm,
in the tau equation.
yeah, we have
Tau
to put
or
it in the tau.
tau, yeah, tau. Actually, there CA naught is outside, and
Yeah,
the integral is from 0 to 80, that is zero point 0.8. And
yeah,
the numerator it will be dxa, and denominator it will be k into ca naught into 1 minus xa whole square.
yes, yes,
Okay, so that we will first integrate this terms like with respect to x, then
hmm,
apply the x, then find a value. So here actually the common terms ca naught, k, all this will be
cancelled
like
out. It will
cancelled out.
cancel. Yeah, yeah,
So then only k tau will be there.
yeah. K tau will be.
K
Actually,
tau.
Yeah, K tau will be there. Correct.
So k tau, that is, so only thing we are like 1 minus xa whole square. We have to, sorry, 1 divided by 1 minus xa whole square. We have to integrate and put this value k tau. And the same thing we have to equate with 0 to zero point 0.5.
Yes, sir, exactly. Actually, sir, K will also cancel out because it's a second order reaction from going from P to Q for both the cases. So the rate constant will also be the same.
Okay, because that rate equation RA is k into ca square. In the
Yes, sir.
tau, we don't have any k term.
Actually, sir, K will also be same for both reactions because it's the same reaction. We are just checking it at different conversion
Okay,
times.
okay. So the rate constant is same. So
Yeah.
that gets cancelled out. Okay.
Yes, sir. Yes, sir. That will also.
So here then we have to put it as the ratio. So the question is like ratio of these two.
Exactly, sir. Yes, sir.
So
It will be like a
okay, okay,
ratio.
fine, fine. Got it. Clear, clear. Okay, thank
Yes,
you, thank you.
that's yes. So in the next question, it's similar. Just instead of the PFR, we are replacing it with the three CSTRs of the same volume. Then the exit conversion of the reactant A is. So in this case, what is happening is uh, all the parameters are same. It's just that our PFR has been replaced with three CSTRs. So the design equation will change from PFR to the CSTR1. So we have to arrange it for three different CSTRs in series. So we have to write this down for CSTRs in series and then equate accordingly to get the exit conversion of the reactant A. For that, you have to calculate. So how can that be done is since we have the reactor right here, uh, we can see like we can arrange this reactor in series three times, and then the flow rate which is coming out of the first reactor will act as the feed for the second, and vice versa, it will go for the others. One simplified expression for this will be 1 by 1 plus tau 1 plus tau k power n. That will give you tau c naught power n. That will give you the expression for the uh, tanks in series design for the CSTR. So if you take a look at that, it will be shown in the notes from the professor also. So from there also you can get it. CSTRs in series will have an expression similar to that. And when you substitute accordingly, you will have the value for the exit conversion of reactant A. So this is a bit of an arithmetic problem. So we will
Yeah.
have to go through the yes, sir. We will have to go through the notes from Sir actually for this.
Just to clarify, now
Yeah.
the equation says only one information, like we are having three CSTR.
Hmm.
The other data we have to take from the earlier.
Yeah.
So earlier also like okay, because conversion only is discussed earlier,
Yeah. Yes, sir.
time with respect to time. So here we are having 1 by 1 plus tau into Ca naught.
Yes, sir. 1 by 1 plus tau into C.
Okay, okay, okay. So like three reactors in series also with Ca naught initial concentration, how we will find?
Uh, Sir, we can use the information from the previous one, like all the expression and the time required for both the conversions is given. So that will be the same, and that will be equivalent to how much it is converting for the same PFR, because we can replace CSTRs in series with a single PFR. So that's how we have to proceed with this.
Okay, okay, because some I think I am not getting it clearly because I don't know whether my understanding is not clear because actually now we are having a PFR. Last question we got two answers. Maybe one is with respect to the tau for 80% conversion. Another one is tau for 45% conversion. Like two values are there
Yes,
for
sir.
zero point 0.8 and 0.45 in terms of seconds.
Hmm.
So that is there. And second thing is that CA naught, that initial CA naught,
Hmm.
we can calculate. Okay, that also we cannot. directly get it.
Yeah, like we cannot directly get that. We have to just get it in terms of it.
Okay, okay,
Yes,
okay. That is
sir.
CA.
And sir, the expression is like this. X is
Okay.
equal to 1 minus 1 by 1 plus tau k power n. And
Oh,
n
it's
is the,
CA.
yes, sir.
Okay, okay.
Yeah, tau
1
k
minus
power n,
tau k
power
whole.
n. And
Okay,
n is the number of reactors in series.
okay, okay, okay. Number of reactors in series. Then
Yes, sir.
definitely the tau k we can get from the other one.
Yeah, yes, sir. Tau, tau we have already, yeah, tau k we can get from here. Yes, sir. We can get the tau k term easily from here.
Okay.
Yeah.
Then it is a direct from there we can substitute with the n as 3, we will get the answer.
Yes, sir. Exactly. We can get.
Okay, 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 thank you.
Yes, sir. And similarly, what you can do is, if you want to write it in terms of disappearance of your reactant, we can write it as K Ca naught or Ca, whatever the desired like variable is equal to K multiplied by Ca naught divided by 1 plus tau K power n. 1 by K Ca naught divided by the 1 plus tau K power n. Again, this is the expression for the CSTRs in series. 1 plus tau K power n. It's the same as above. It's just that for the in the above expression, what we were seeing is the conversion. Here we are writing it in terms of disappearance of A or disappearance of P, whatever you can write.
Rahulji, your voice is breaking. Anyway, I'll just repeat once again that KCA equal
Yeah.
to
Yes, sir.
K.
KCA is equal to K multiplied by Ca divided by 1 plus tau K power n.
Oh, okay, okay, fine. So left also is KCA is there, and right also we are having KCA divided by 1 plus tau K whole power n.
Yeah. Yes, sir. Yes, sir. We can
Okay,
write it
okay,
like that. Yes, sir.
okay, okay.
Yeah. So when we perform that specified arithmetic, we'll be able to arrive at the answer. Moving on to the next question. For equilibrium considerations in closed systems, the relationship in between the degree of polymerization Xn and equilibrium constant K can be represented as. This reaction scheme which I have shown here is directly from Search notes, or you can see it in the lecture classes itself. Here we have been given a rate constant K is equal to the concentration term for COOH multiplied by H2O divided by COOH multiplied by OH. So here for the equilibrium constant, we can write equilibrium constant as the rate constant of the particular reaction when we can define it as the ratio of the forward reaction constant divided by the backward reaction constant. So this is the polyesterification products from uh, a polymer. So we are doing the esterification reaction and we have the COOH group and H2O and COOH group and the OH group right here. So we have represented that as CE, that is CE is the equilibrium multiplied by the CO naught, CO whole square. And this notation you'll be able to find it in source notes properly. And from there, we are arriving at the relation that Xn or the degree of polymerization is equal to 1 plus K power half. This relation defines that the equilibrium constant should always be in the direction of the polymer. Direction of the polymer means that it should always support the reaction to move forward, and it should always be shifted towards the larger molecular weight polymers, so that the degree of polymerization always remains high. So that's why the answer of this question is the first one. I think it will be better if we like, if you take a look at the search notes for the week 6, because in that he has explained the step growth polymerization, and this is from that actually. So
Okay.
the
Okay, probably the next week I need to go through. Just to clarify, here.
Yes,
This K we are referring it as equilibrium constant. It is not rate constant. And degree
yes,
of
sir.
polymorphism is 1 plus like square root of K.
Yes, sir.
That
Square
is
root of it.
okay.
Yes, sir.
Okay. And
Mm.
Ce and Co are the equilibrium concentration of this COH.
Yes, sir.
Okay,
Yes,
okay, okay.
exactly.
So here
Yeah.
it is like acid ester, acid alcohol means esterification reaction, something like that.
Yes, sir. Exactly. It's an
Okay,
esterification reaction, and it's forming the alcohol, and acetic acid COOH group is there also.
okay, okay, okay,
Yes.
clear. And
Yeah.
just because sometimes one clarification is there equilibrium constant, like when, like how we can find out like values that is from that top equation, like what we have seen C square by 1 minus C whole square,
Uh, like when no,
equilibrium
sir.
constant.
Actually,
For,
sir, equilibrium constant will be given in the question most of the
okay,
times.
okay, okay, fine, fine, okay.
It will be given because that's very difficult to calculate, and equilibrium constant will be given in the question.
Okay, okay, fine, 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 fine.
Yes.
Thank you,
Yeah.
thank you, thank you.
It is important to remember these relationships so that you can interconvert easily. Like if you have been given the degree of polymerization, you can arrive at the equilibrium constant, or vice versa. You can do that.
Okay, clear, clear. Yeah.
Yes, sir. Next question is, which of the following statements is false for the importance of solvents in polymerization process? In the presence of a strongly protic solvent such as DMSO, higher molecular weight polymer can be obtained. First statement is this. Second statement is it helps in the accessibility of functional groups with the reduction in viscosity of reaction mass. Third statement is it influences the rate of polymerization and molecular weight due to the preferential solvation of relationships with either the reactant or the transition state of the reaction. So we have been asked to find out the false statement for the importance of the solvents in the polymerization process. So first statement is in presence of strongly protic solvents such as DMSO. Since DMSO can produce H plus ions, it is called a protic solvent because it is forming the proton. That is the proton donor. So that's why it's called a protic solvent. Higher molecular weight polymer can be obtained. Now, what happens with strong protic solvents is that it is able to dissolve the uh, polymers in a much better manner. So the handling becomes easy, and it allows for more polymerization to occur. So that's the reason why higher molecular weight polymer can be easily obtained because of this. And since this is a protic solvent, the amount of hydrogen joining onto the backbone will also be uh, more efficient. Second point is it helps in accessibility of functional groups with the reduction in viscosity of reactions. This is quite obvious that when the polymerization is quite high, the reaction mass or the product which is forming will be extremely viscous in nature. And reduction in viscosity will help the accessibility of the functional groups. Why? Because the end groups should be available on the active sites so that the accessibility will be better and the polymerization can proceed further to obtain higher molecular weight polymers. So these two statements are correct in the sense like these are not false. Third one is it influences the rate of polymerization and molecular weight due to differential solvation or relationship with either reactant or transition state. Now, solvents in polymerization processes are used in such a way that they're either able to dissolve the reactant itself, as in the monomer itself, or the transition state reaction, or the polymer which is formed. The reaction mass or the final polymer which is obtained can be easily dissolved into the solvent itself so that the handling or the preferential solvation is much better. Because of this, the molecular weight can be controlled, as in higher molecular weight can be obtained, and the process becomes much more simpler because of the use of solvents in polymerization process. So none of the above will be the correct answer because all three statements are true, and we were asked to find the false. Next is the kinetics of the polymerization process is important for. First is to understand how is the reaction proceeding over time. That is the main job of the kinetics. Third is to define the reaction mechanism and how the rate constants and equilibrium constants are defined. with respect to the kinetics and the rate of the polymerization. So all of the above is the correct answer for this. The step growth polymerization process reaction begins rapidly, but higher molecular weight is obtained slowly at the end of the process. This is true because in step growth polymerization, the polymerization process occurs when the monomers are attached one by one, and the chain grows longer and longer. As the monomer attaches one by one, like as the reaction proceeds further, that process will be quite rapid, but the ending of the chain will occur only at the last stages of the process. So that's why it is true that the step growth polymerization process reaction begins rapidly, but higher molecular weight is obtained only at the end of the process. The polycondensation can be
Generally,
carried.
sorry,
Yes,
just to clarify, the step growth generally we are like condensation reactions, right? Like phenol formaldehyde.
yes, sir. Yes.
Yeah. So in the case, like initially it will be exothermic generally when we
Hmm.
do that reactions.
Yes.
So it will add up very quickly, but the molecular weight buildup will be slow at the end of the process. That is the point.
Yes, sir. Exactly.
Oh, okay, okay, fine, thank you.
Actually, when the reaction is very rapid in the beginning, what is happening is a lot of polymer is forming, but that polymer is going to act as an insulator. So all that thermal energy won't be utilized much more efficiently. That's why the process slows down. It will begin rapidly, but it will slow as the higher molecular weight is obtained by the end of the process. It's something like that.
Yeah, yeah, thank you.
Yes, sir. The next one is the polycondensation can be carried out with the help of various polymerization techniques such as. So we have been given here three options, and if we have gone through the class material, we can clearly see that all of them can uh, perform the polycondensation process easily. That is the solution polymerization, solid state polymerization, and the emulsion polymerization process. So we can see that even in emulsion polymerization, we can easily separate the water out with the micelle formation, and the initiator is present. So it will polymerize the monomer molecule itself, and you can see how the polymer is being formed inside the micelle formation. And on the right hand side, you can see how the condensation reaction works. We have two chains here, and we have the OH group, H2O, OH group coming out as an H2O, and removal of the water molecule forms the entire polymer right here. So this kind of condensation reaction can be observed in all three of the polymerization reactions. In all of them, the average molecular weight obtained in the step growth polymerization is limited by. So the step growth polymerization reactions in the step growth polymerization are governed by certain factors. So here three of them have been listed. First is rate of the reaction, second is reaction equilibrium, and third is the rate of diffusion. So in step growth polymerization, as the chain increases, we know that the kinetics of the reaction is slowing down. So the rate of the reaction as time proceeds will slow down. The rate will go down. And as it goes down, it will reach the equilibrium. Now, how fast it reaches the equilibrium, or uh, how well we can push it past the equilibrium or bring it back onto the polymer side, is what defines the average molecular weight obtained in the step growth polymerization. That's why the reaction equilibrium is much more important than the rate of the reaction itself. Because shifting of the reaction equilibrium defines how the rate of the reaction will proceed. That's why reaction equilibrium is always much more important than the rate of the reaction. And here in this case, rate of diffusion does not have much role to play because we don't essentially have anything diffusing into the other. So in step growth polymerization, reaction equilibrium plays a major role. So reaction equilibrium governs the average molecular weight obtained in step growth polymerization.
Just to clarify, this
Yeah.
reaction equilibrium, what we are referring is that from conversion from raw materials to products through
Yes,
forward.
exactly. Yeah.
Okay. Other one is rate. Anyway, rate average molecular weight is not limited because of rate.
Yeah.
And okay,
It's not
that's,
limited. Yes.
yeah. And the same, the limiting factor is only the reactionability. Okay, okay,
Yes.
okay.
Yes. The next is the viscosity of the reaction solution increases significantly with the increase in conversion. So the removal of byproduct molecules from the viscous mass becomes a process of rate control, important to obtain high molecular weight and pure polymer product, both A and B, and not an important process. So when the polymerization process is occurring rapidly, at the same time, there are some undesired products being formed that are the byproducts. So when the viscosity is increasing for the reaction, it becomes very important uh, to like open up the active sites. So because the byproduct is also forming simultaneously, so it will become the process of rate control, the operation of removing the byproduct. So the viscous mass, when it is produced, we have to remove the byproduct, and the faster you remove the byproduct, the higher the molecular weight will be achieved. So it definitely becomes a process of rate control, because if the removal of byproduct is slower, the entire reaction rate will go down. So it definitely is a process of rate control. Second is important to obtain higher molecular weight and pure polymer. If we are going to eliminate the byproduct itself, definitely the polymerization process will be much more efficient and we'll be able to obtain the higher molecular weight. So that's why both A and B are correct in this. Next one we have the application of interfacial polymerization is useful in the manufacturing of reverse osmosis for encapsulation of inks, insecticides, and medicines. So in reverse osmosis, how interfacial polymerization takes place is that the interfacial layer where the reverse osmosis through which the reverse osmosis is taking place is very important, and then the interface at which the reverse osmosis process is occurring is very detrimental for the interfacial polymerization reactions for encapsulation of the inks. So interfacial polymerization reaction is basically separating two different phases. When we want to separate two different miscible immiscible phases, that is the stage where we are going to use the interfacial polymerization process. So in encapsulation of inks, if we are trying to disperse it in some, like if we want delayed dispersion, or if we are trying to separate the ink from water or vice versa or any other process, to form the interface between the ink and the material in which the ink has been uh, put, we have to use the interfacial polymerization techniques. Insecticides and medicines, again, the insecticides also form a polymer layer on top of the plants or any of the fruits, because of which the outer environment cannot come into contact with the surface of the plant itself. And the same can be done for the medicines. So all of the above. These are mostly like you will be able to read it through the notes of Sir, and these are more like general information about the polymerization processes. So with that, uh, today's class is wrapped up actually.
Rahul, small clarification. Just
Yeah.
with respect to that application, interfacial polymerization reverse osmosis is like a separation process only, not like where the polymerization aspects comes into picture.
Yes. Yes. Exactly.
So it is like we are separating, say, salt desalination. We are using RO to retain this, say, salt crystals on one side, and the osmotic pressure it will come this side. So do we need to consider that also as a part of polymerization? Anyway, as you told, it is like an interface only. This is happening.
Yes, sir.
Okay, okay. Encapsulation of inks, I understand. Yes, it has to be in interface.
Hmm.
Insecticides and medicines, insecticides also, like it is like whatever we are talking about is something like pesticide is different, insecticide is there, and medicines. Okay.
Yes, sir.
Okay. Which means all three, all four, all three are part of interfacial pollination.
Yes, sir. All clear part.
Okay, okay, Thank you. Thank you.
Yes. As the classes move forward, it will become more dependent. We'll be going more into the methodology of the polymerization process and what are the individual factors which control the polymerization reactions. So these are in the beginning basics of the reaction engineering itself, the basic CRE sir has taught us in the lectures itself. And so from moving forth from here on, it will be more about the polymerization process itself. So, sir, if you have any
Yeah.
doubts, you can
Yeah.
ask. Uh,
Yeah,
for,
one clarification I would like to
yeah.
probably now that graphical representation when we are representing different types of reactors like batch, mixed
Hmm.
flow, and blood flow with
Yes,
respect to one is with respect to reaction rate, another one is with respect to conversion.
yes,
Like a easy way where we can understand is possible to give like for these three type batch, blood flow, and mixed flow. One is with respect to reaction, 1 minus RA, 1
yes,
by
sir.
1 minus R with respect to the time. Another one is the conversion, variation of conversion.
Hmm. Yes, sir.
Uh,
You are
uh,
asking like how to understand it properly, or like
yeah, how to like quickly from a representation, how we can understand this is PFR, MFR like that, or how we can graphically represent in a fast way, like a quick understanding.
okay. I think much better method will be like trying to make the residence time distribution. You can do that because the
Okay,
residence time distribution of a CSPR and a PFR are very different. Why? Because as we know that in CSPR, everything is in mixed flow. Everything is being mixed instantaneously. So the moment you put it in the inlet, in the outlet also, you're going to give the same concentration instantaneously. So that's why if you are going to put your tracer in the inlet, your outlet will have the similar tracer at the same time. So the residence time will be almost nil because the mixing happens so fast in an ideal case I'm talking about. Uh, so the function for that will be it will be like an it will be like a impulse function. It will be suddenly showing the impulse for that. After this,
Same way like this concentration also will drop down very fast since it is mixing. Is it
exactly,
like?
yes, sir, exactly.
Okay,
That's the
okay.
meaning. Yeah, because the concentration drops down very fast. And in case of a PFR, since it's a long tube, uh, across the length, the concentration will decrease like that. So the tracer concentration will follow the exponential curve in a similar way how the concentration decreases.
Okay, okay, clear.
Yeah,
Yeah,
like this. So concentration profile itself inside the reactor can tell you much better about how things are.
yeah, exactly. Yeah, yeah. Because
Yeah.
that's for understanding. Maybe easy way we can catch from the plot.
Hmm.
Yeah,
Yes, sir. Yes. So if you were to plot the concentration profile inside a particular reactor, or if it's been given, so you can see the nature of the curve itself and tell what kind of reactor it is.
sure, sure. Yeah, yeah.
Yes, sir.
Thank you. Thank you very much.
Yes, sir. Okay, sir. So today's class is over. So don't have any doubts. We can end it here.
Yeah, actually, like now I am in the. I completed today only the all the fifth, and I uploaded my assignment also for this week.
Oh, okay, sir.
Since parallelly I'm doing other classes, some three additional courses also there. So
Oh,
that also parallelly, like it is like four courses parallelly I'm doing now.
okay,
So
okay.
that like that is going on. So that's why once I complete that full set by today, like tomorrow is the last date for the other assignments also. Probably that once I finish it, then I go for the next week. So whatever now today we discussed, I think most of it is covered in the upcoming session. I think
Yes,
the
sir.
step corporation all are covered
Yes,
in the
sir.
next.
Yes, sir. Yeah.
Okay, okay, okay.
Most
I'm
of
just.
these things which I
Uh,
discussed today was it will be in the week six, kind of like week six
oh,
lectures.
okay, okay. Thank you, thank you. Anyway,
So
just to
yes,
clarify. Yeah,
okay, sir. If you have any doubts, you can watch these lectures on online also, because this interaction will be uploaded on YouTube also.
Okay, okay. Maybe that initial whatever we discussed that can be cut because that is internal discussions. So
Yeah,
probably.
yeah, yeah, yeah.
Yeah,
Yes, sir.
yeah, yeah. Okay,
Okay, sir.
okay.
Okay.
Thank you so much.
Yes.
Thank you. Bye. Okay, bye.
Yeah. Bye, sir. Bye.
Thank you.
Yes, sir.